Olá, boa tarde a todos. Bem-vindos ao ciclo de seminários do Departamento de Geofísica do IAG-USP. Hoje a gente tem o prazer de receber a Yeva Gevorgyan. A Yeva, ela fez bacharelado em Física pela Universidade Estatal de Yerevan, mestrado aqui no Instituto de Física, na área de teoria de cordas. Depois ela fez doutorado em Matemática Aplicada no IME, já nas áreas de Mecânica Celeste e Geofísica Planetária. E atualmente ela é pós-doutoranda no IME, e esse ano ela está fazendo um estágio BEP da FAPESP no Lunar and Planetary Laboratory, da Universidade de Arizona. Bom, a Yeva entrou em contato com a gente porque ela está submetendo um projeto para a FAPESP, e daí a gente achou que seria interessante ela apresentar esse seminário aqui no departamento, que tem relação com o Departamento de Geofísica também. Então, Yeva, muito obrigado por aceitar o convite. Pode ficar à vontade quando quiser começar a apresentar.
Obrigado, Gabriel. Obrigado pelo convite. Eu agradeço muito por essa oportunidade de apresentar meu trabalho no IAG, que é um público novo para mim, que às vezes eu atendo seminários, etc., mas nunca apresentei meu trabalho aqui. Então, vou começar a minha apresentação. Aqui, só um minutinho. Dá para ver? Dá para me escutar direitinho? Só para começar. Tá bom, obrigada. Então, hoje eu vou falar sobre meu trabalho. Eu vou apresentar o trabalho em inglês, então eu vou passar falando em inglês. Today I'm going to talk about the work that I did during my PhD, and I'm continuing to do it during my postdoc that I started 2 years ago in Brazil, and now continuing at the University of Arizona. I'm going to talk about viscoelastic behavior of simple multilayered and homogeneous laboratory-based rheological models for moons and planets in our solar system, and for extrasolar planets also. What kind of questions we are interested in our research is to explore the applicability of effective Rheological models to models otherwise stratified bodies, as it's well known from the data. Our Earth is pretty much stratified with 6 or 7 layers. The Moon, the Mars, and other planets that we have data are very likely stratified. But since we have little access to little data for other planets, even in our solar system, and we would like to look under their surface, we need some effective models to be to represent their behavior with fewer parameters, since we have little data to fit them. So another thing that we are interested in is to predict core-mantle mechanical decoupling from measured librations of celestial bodies, since this could give us a glance under the surface of a body, because mechanical decoupling could advocate for the presence of a global subsurface ocean for icy moons, for example, or for a liquid core, like the case of Mercury, for instance. And another question we're interested in, it's to mimic the dissipative behavior of otherwise stratified body using simple models, and to see for which range of parameters and for which kind of rheologies this is possible. So I'm going to do a small introduction to tides, librations, and dissipation today, when I will introduce the formalism that we use to model the deformable bodies and their orbital motion. And then I will talk about many examples and introduce the rest of our formalism, in particular examples of Enceladus, one of moons of Saturn, and TRAPPIST-1 planet also, which is an exoplanet in a system that people say that has planets that are Earth-like and possibly could support life. So it's these planets are well common to study in literature, so it's one of the examples. And also, I will consider our own moon. for the dissipation of our own. So tides, I'm just gonna, a simple explanation for tides. It's since all the real bodies that we consider are not elastic. When we have we consider a two-body problem with Saturn, in this case, as a point mass, acting on Enceladus, one of its moons, with no consideration of other bodies. In a planar case, we can see that, Enceladus is tidally locked with Saturn, so Enceladus always shows one of its faces to Saturn, exactly the same way as our moon does. And Enceladus is in an eccentric, slightly eccentric orbit, since it's tidally locked with another satellite of Saturn, which is Ion. But so we don't consider this body, but we consider an eccentric orbit for Enceladus. And in this case, when Enceladus is the line that connects Enceladus and Saturn, in that direction, Enceladus is always deformed a little bit more due to tidal force, gravitational force from Saturn. And so this deformation in the next moment, when the other part of Enceladus is connected to Saturn, the deformation persists, since Enceladus is not is not perfectly elastic body, so this deformation persists for a certain time. And this creates a tidal lag and torque on Enceladus, which diminishes the total energy of orbital energy of Enceladus is lost in every cycle. And this energy loss is proportional to the tidal lag that we see here, since the deformation is not, since the recovery of the shape of Enceladus is not instantaneous. So this tidal lag can give us information on the internal structure of a body, since it depends on the viscoelastic properties of a body, and the time that it takes to recover its original shape could tell us what is the body made of. Another important quantity that we look are tiny oscillations around the synchronous rotation of a body, which are called librations. These librations can be directly measured for some bodies. For instance, for Enceladus itself, if we have a spacecraft around it, and we could measure from the surface the librations, and this could give us a clue on, for example, the existence of a subsurface ocean for a body. So the librations, what's the importance of librations for us? For distant bodies, the only way of looking under their surface is through their dynamics, rotation dynamics, and librations is one of few observable quantities. So if given the amplitude of these librations, we could argue that the crust is decoupled from the core, and the body is, and there is a global subsurface ocean, for instance. So it's important to have a model between the librations, the amplitude of libration, and the internal parameters of a body. Another important thing about librations that they also increase they contribute to the total energy dissipation that we observe for bodies. That's another measurable quantity, which is proportional to the perturbation in the gravity of a body. So now I'm going to present the assumptions that we make on deformable bodies in our models. So if it's an isolated deformable body, it has to have a mass distribution which is spherically symmetric if it's not rotating. If it's rotating, the mass distribution is almost spherically symmetric, where density levels are approximately ellipsoids of small eccentricity. The body material should be incompressible under small deformations. And the internal forces should preserve total angular momentum. For a system of deformable bodies, we should preserve this second assumption, so spherical symmetry. The body should be still almost spherically symmetric, but distances should be such between the bodies such as this assumption is preserved. So the deformation in this deformation of a body in this case is presented by the infinitely many degrees of freedom. And it's important to choose a right body frame in which equations can be integrated with this. And here in this case, the body frame that we choose is a Tisserand frame, which is the frame in which the total angular momentum of a body is preserved. So for an isolated deformable body, the Lagrangian can be written in this form, where I0 is the mean angular momentum of a body. Omega is, all the quantities in bold are matrices, so this is all in matrix notation, all these equations. Omega is rotation matrix for the body, and B is the deformation matrix. Mu is inertia constant, and gamma is gravitational constant of a body. From this Lagrangian, the equations for the body can be derived. So quantities are the same, and here Y is a transformation from the rotation matrix from the inertia frame to body frame, and L is angular momentum of a body. So now, B is the important quantity that was introduced in our formalies. Here, B is a non-dimensional matrix that can be interpreted as a non-dimensional quadrupole momentum of a body. It's traceless and symmetric. Since B is very small all the time, since the body remains spherically symmetric at all times, we can present the inverse of angular momentum as this. So this formula. So now if we consider a deformable body and a point mass acting on it, the Lagrangian has this extra terms due to gravity, and here the M1 and M2 are respective masses of deformable body and a point mass. And so from this Lagrangian, we can derive the equations of motion for the dynamical part of the equations of motion. And at this point, what we need are the equations for the transformation, for the deformation of a body, equations for B. So the introduction of these equations is an important part of our work, and it was done through so-called association principle. To use this association principle, we need to represent the body as in terms of a general oscillator, where gamma can represent the gravity, self-gravity of a body, mu is the inertia, F is the force acting on a deformable body, and here this rheology part can be replaced by any rheology. It can be a simple one, like Maxwell, for instance, which has this elastic and viscous elements, just two of them, or Andrade, that's more complicated one that has 4 parameters normally, and can be even more complex, like 6 parameters for Sandberg-Cooper model. These models have can be here, for instance, we have 2, 4, or 6 parameters. This is still far less parameters than what we would have if we model the body with a multi-layered structure, instead of considering a homogeneous body with an effective rheology in this case. And we have less parameters to fit, and it's much more convenient to work if we are looking into distant bodies. So this rheology also can be, in terms of our formalists, this rheology could be in principle replaced by a rheology with multi-layers, where we have a stratification for the body. But for now, let's think of this effective kinds of rheologies. So how do we change from this kind of general oscillator to a deformation of a body? So in 2017, Ragazzo and Ruiz formulated a so-called association principle that states that if we change the differential equations for x by the differential equations for the deformation, we can do this just by replacing x by b, where b is the deformation and x is just the displacement of oscillator. In this case, we will obtain the equations for deformation. So when I'm going to go to a particular example of Enceladus and show the equations for the particular case. Why we choose Enceladus? Because it's one of more mysterious moons in our solar system. During flyby of 2005, Cassini mission found a rupture in its south pole, which indicates the presence of a subsurface ocean. And from librations, from libration, we can tell that probably Enceladus has a subsurface ocean. So it's an interesting example that can be studied. It's very likely that it has a decoupling between its icy crust and the core of it. And the dissipation energy measured for Enceladus is also anomalous, and it's pretty large for such a small moon. So there are many questions. Some are answered and some yet to be answered for Enceladus. So here we consider motion of Enceladus to be planar, and just consider two bodies, Enceladus and a point like Saturn. And in this case, the equations of motion in the inertial frame can be written here. This is the dynamical part of the equations, again, total angular momentum. And now to model Enceladus, we choose Andrade rheology here. So rheology was put into a general oscillator. The Andrade rheology has 4 parameters, as we can see, and our equations are normally written in the time domain, and our integration happens in the time domain. The importance of Andrade rheology here is that it had been used already before to model celestial bodies, but the difference is that normally Andrade rheology is used in frequency domain, because this element brings us to integral differential equations in time domain. So our contribution was to show that Andrade rheology actually could be replaced by a generalized void model, with Andrade element being replaced by infinitely many elements of void type, which are easily represented in time domain, when we could show that the number of these elements is finite. So we can have a system of finite system of equations to be integrated, and even further, we could show that with as few as 6 oscillators, for instance, here we can have the same effect as Andrade rheology. The importance of using Andrade rheology and not directly using the generalized void model is that generalized void model would have 2n plus 2 parameters to fit. But if we if it's obtained from Andrade rheology, all 2n parameters of void elements depends only on 2 parameters of Andrade rheology. So we still have 4 parameters, but we are able to integrate the model in the time domain. So the equations of deformation for Andrade rheology in the time domain are these ones, where n in our later integration n should be 6. These are all matrix equations. So for each equation, there are actually 5 linear equations. And so the advantage of using Andrade rheology in time domain, that we are not using a perturbation theory to treat the problem. And so we are not restricted to small eccentricities and small mutual inclinations. So we really can go to large eccentricities and inclinations, and we are not limited to quasi-periodic perturbations. And also where the motion can be totally 3D. Here it's considered as planar case, but we are not restricted to this. So using these equations, ones for dynamics and ones for deformation here, we could obtain the amplitude of libration for Enceladus. This comes from integration. The blue one is mean amplitude of libration, and we get a libration of 5 times 10 to 4 radian. The red line here was obtained by a formula that we also obtained in our paper. That is, it's an analytical formula to find the librations. And here you can see that it's in an analytic formula, and the integration results are in very good agreement. And so both can be used for analytical formula can be only used for simple planar cases, and the integration is not restricted to that. So here, so now we would like to compare these obtained librations for Enceladus with observed ones. The two suggested observations, there are two suggested observations for the libration of Enceladus, and one of them shows a libration of 2 times 10 to minus 3 radian, and another one 2.7 times 10 to minus 3 radian. So you can see that the librations we obtained are 4 to 5 times smaller than the observed ones. We can explain this by the fact that indeed Enceladus is not a homogeneous body, and it has a decoupling between the crust and the core. And so if we assume a 3-layered internal structure for Enceladus and give a tiny possibility of tiny librations to a core, which is just 0.6% of that of a shell libration, we can reproduce the crust of our 3-layer model would librate with the same amplitude as the observed one, and the total body, the effective body, would have the librations obtained by our integration. So this brought us to at this point we decided that we need a different model, at least with 2 layers. I first will talk about the dissipation. So the dissipation part, the dissipation equation was derived for Andrade Rheology here, and this equation is in good agreement with other equations in the literature. And here you can see that we have a contribution from librations, this beta part. And since our librations are smaller than the ones really observed, the increase in dissipation is not that large. It's around 7%, but still we show that it's important to consider librations when we are talking about energy balance for Enceladus. And so from integration, you can also see that we obtain the total dissipation of a body is around 10.5.6, so it's more or less the same value as the theoretical one. And so partial results here, that numerical and analytical results of our paper are in good agreement. This approach allows us for consideration of chaotic motion, transient events, and resonant librations also. Triaxiality appears naturally in our numerical integration through libration, because we initially don't put any assumptions on the triaxiality of a body. We can capture increase in dissipation rates due to librations of around 7%, but if libration increases, this contribution could be much larger. And we also conclude that homogeneous rheology is not enough to reproduce observed libration of a body that has a global subsurface ocean, because the observed librations are actually ones of a crust of a body and not of total body. Now at this point we started thinking to make a more complex model to be able to reproduce the librations of a crust. So we have to separate the crust from the rest of the body. And here we are trying to answer a question if that would be enough, not having like 3 layers, but just 2, a crust and effective liquid layer underneath it. to obtain the librations measured for Enceladus. Here, this will be done by considering the librations of crust and also of effective body and comparing them to the measured librations, depending on closer to each of obtained librations the measured one is, we can argue that the body either has a subsurface ocean or not. And so we'll use the core force libration amplitude as an argument for core-mantle decoupling or a presence of a subsurface ocean. So here we, for the mantle, in this case, we consider a simpler rheology. So the mantle is represented by this rheology. We have, and everything underneath is represented by a liquid body. With effectively the core and the ocean of Enceladus are incorporated into this one liquid body. We can, in the same way as before, we could write the equations of motion, and by integrating the system, we obtain following librations. So libration amplitude that now we obtain for the mantle of Enceladus is around 2.7 times 10 to minus 3, which is in perfect agreement with one of the measurements. Of course, by adjusting the parameters, we probably could get closer to other measurement also. But here, the important part is that indeed, when we have two layers, we can have librations that are much larger than our initial librations, around 5 times. And so 2 layers are maybe enough to represent a body that has this internal mechanical decoupling between its mantle and core. Here you can see the libration amplitude of effective body or the Tisserand frame, librations of a body frame. So these librations are like compatible with the effective body librations that we obtained before. And yeah. Okay. So about so indeed, the libration can be used as an argument for a presence or absence of a subsurface ocean, or a presence of a liquid core, like the case of Mercury, for example, that has a crust on top of a very large liquid core, where the crust can librate on top of liquid core. About dissipation, so in this case, most dissipation, for this two-layered model, most dissipation occurs in the mantle. And the dissipation that occurs at boundary between the mantle and the liquid inside is pretty tiny. If you can see here, it's 10 to minus 6 compared to 10 to 9 watts dissipation rate. So that can be discarded, the core-mantle boundary dissipation. So the increase in dissipation rate due to forced librations is in a good agreement with the first part, where the dissipation of the effective body was the same in both cases. And since now the libration of a mantle is much larger, the contribution from libration is around 40%. So yet another argument for not discarding libration dissipation when we're studying problems of dissipation. So now I'm going to go to the next problem that we consider here. It's now we go to bodies that don't have internal decoupling between the crust and the core, so they don't have a subsurface ocean. They are Earth-like planets or moon-like satellites. And so here we want to see if, at least in this case, it would be enough to consider a homogeneous body to represent otherwise stratified planet or satellite. We want to see how well can we mimic its dissipative behavior. And we want to establish a connection between the parameters of a stratified body and effective rheology parameters. Here, as an example, we pick TRAPPIST-1a planet with one of its possible structures, where it's assumed that it has a icy cover on top of its surface. So it's here it's considered to have 5 layers, a liquid core, 2 mantle layers, and 2 icy layers. The presence of icy layer changes qualitatively the behavior, dissipative behavior. The dissipative behavior of TRAPPIST-1a. Here you can see, so this is the imaginary part of love number that is basically dissipation of a body is proportional to imaginary part of a love number. You have a frequency dependence of dissipation. And so here you can see that if for this 5-layered structure of TRAPPIST-1a, the curve is here, it has 2 bumps, and the second peak here is due to presence of ice layer. In case, if we consider a structure, Earth-like structure with no ice, the behavior has just 1 peak, and that in paper by Beaumont et al. Of 2020, they claimed that so for Earth-like structure, they could reproduce the multi-layered behavior using homogeneous Andrade model, since it had just 1 bump, but they claimed that in the presence of ice, they have this second peak, and that was not, and they were not able to reproduce this behavior using a homogeneous body. And this was used as an argument for need to use multi-layered models if you are looking into dissipation. But on the other hand, if we try to fit this using Andrade model, and in our recent work, we just added 1 more element to Andrade model, which is a void element here. This model is known as Sandberg-Cooper Rheology. And using this kind of rheology, we could reproduce perfectly their data with 5 layers. And these curves were in perfect agreement with their curves, and they are done by they are reproduced by a homogeneous rheology with Sandberg-Cooper element here for the body. So this Sandberg-Cooper rheology has 6 elements, 6 parameters to be fit, compared to at least 10 parameters from the 5-layered body. So we have advantage on less parameters to be fit for a body that is TRAPPIST-1a, but we have very little data at this point. We may have at some point measurements for K2 and similar stuff, but for now, it's very advantageous to have fewer parameters. So another example that we consider here is our moon. For the moon, there are more or less 2 possible internal structures. We go with a simpler one, but that doesn't change much our arguments. Here we consider a 4-layer rheology, 4-layer structure with a solid core, liquid core, mantle, and crust. For a moon. So using this 4-layered rheology, we could obtain the dissipation curve for the moon. This green curve here in the figure was obtained for a 4-layer moon. And so we try to reproduce this curve using some kind of homogeneous rheology. We show in our work that the general curve for any kind of any general curve can be reproduced with a homogeneous body of this kind, where this is a generalized void model, but it has, as you can see, 2n plus 2 parameters if you have n elements here, and that would be too many parameters to fit. But when we perform frequency analysis on this curve, for a 4-layered model, we can see that only free frequencies are actually important in this case. And you can see with free frequencies, actually the decomposition of like partial fraction decomposition of this curve has around 10 or 12 frequencies, but just using 3 of them, we can have this red curve that you can see here. But yeah, it's like in a very good agreement with a green curve, red one. And even more, so we can discard this part of curve since frequency range this small is not relevant for any geophysical phenomena. So actually we are left just with 2 important frequencies. So this black curve was made by using just 2 frequencies. So this means the number of frequencies is one, it's the number of elements here that we need to reproduce certain dissipative behavior is the number of frequencies minus 1. So we just end up with this rheology. So here we claim that using just a simple Burger's rheology with 4 parameters, we can reproduce the dissipative behavior of a moon modeled with 4 layers. And so here, as you can see, so this red line here is the model with 4 layers, full model, and the blue line was reproduced just using this homogeneous model. So we claim that we don't really need to use multi-layered model here if we are just looking for the dissipation. It's just a matter of choosing the right parameters. And so at this point, we are working on establishing a connection between the internal structure parameters of a layered moon and the parameters of our model, such as in the future, this can be used for distant bodies for which we won't be able to have the same notion of a structure as we do for the moon. So conclusions are, so laboratory-based homogeneous rheologies are important to model bodies with little observational data available. 2-layered rheology can be used to look for core-mantle decoupling in celestial bodies, and so to look for an ocean or a liquid core. And homogeneous rheology can be used to model dissipation of bodies that don't have any mechanical decoupling, and even have independently of what they are made of, even in case of ice or any other materials, we still can reproduce their behavior. So I will just leave some references that you can see more details on my work, and I will stop here. Thank you.
Thank you, Yeva, for your presentation. It was really interesting. Now we are open to questions. Everyone who is watching on YouTube can write there, and I will read the question to Yeva. And what are your projects that you submitted for PASPER continuing to study these rheological models? What are you going to do next year?
No, actually, at this point, I'm trying to migrate a little bit. Actually, it's again about rheological models, studying the internal structure, but I would like to apply machine learning to help with choosing the rheology for the body. And since I want to also apply this study to exoplanets and for which we are going to have like large populations of planets, we would like to have a trained neural network that would be able to predict the internal structure of his body. So, but at this point, I'm still like developing models that can be used to train these neural networks, but the idea is that. And another thing is also to use neural network to identify these librations that I was talking about. So this is actually this work is pretty minuscule. People look at the layers of body and still almost by hand try to identify the librations from some control points on the surface. So this is another problem that could be like automatized. Automatized. Yeah, so we could use neural networks to deal with this also. So actually the project that I submitted for FAPESP is in this direction.
Okay. And, thank you. Okay, there are some questions here. Bom, estão sugerindo de falar em português agora, pode ser?
Pode ser, sim, claro.
Bom, você responde como você achar ficar mais confortável. O Vitor Sasek, professor aqui da Geofísica, ele agradeceu a apresentação. Bom, eu vou ler a pergunta dele em inglês, tá? Porque foi como ele fez. How these results obtained for Enceladus can be applied to other icy moons, for example, Europa? What are the differences or similarities?
Okay, so at this point, actually, I'm working on, that's another study that I'm trying to do, like to see how, for example, the result that I have on looking for a subsurface ocean using the librations. Europa is one of bodies that I would like to apply it because it's the librations of Europa are pretty different from the librations of Enceladus. So it's a kind of study that I'm still working on, and I don't really have like results ready, but that's going to be a comparison that I'm going to do if this argument will still hold for these other bodies or not. I'm really working on it, and I mean the application, the models can be, the results are, most of novelty of results is mostly on is in the modeling part. So it's the innovation of like using Andrade Rheology in time domain and stuff like that. So the results are not really new, but the models can be used for different bodies. That's one thing. Another thing is that we established some connection between the parameters of homogeneous bodies and the stratified bodies. So you could apply this to other bodies, for instance, Europa, why not? And actually, the research that I do is most of when I apply to, at this point, I'm still on the stage of refining my models. So all these bodies that I use, like Moon, Enceladus, etc., are mostly used as test bodies. So it's more like benchmarking than prediction of something else. I still didn't, I mean, I proved a couple of results that are already there in the literature. But yeah, it's, for now, it's mostly benchmarking, and we are refining our model and parameters.
Okay, thank you, Yeva. Just a moment. Okay. Ok, there are no other questions here. Bom, se alguém quiser perguntar também em português, pode ficar à vontade. O Gustavo Gosling perguntou, é entendido o porquê da libração de Europa ser diferente da de Enceladus?
Como é que é? Não entendi.
É entendido o porquê da libração de Europa ser diferente da de Enceladus? Você sabe-se o porquê?
Não tem exatamente uma explicação assim clara por que eles são diferentes, porque modelar, assim, tudo que a gente faz é uma modelagem. Então, também tem essa, às vezes tem que um deles foi modelado de um jeito, outro de outro. Então, eu quero fazer esse estudo, por exemplo, atualmente aplicar o mesmo modelo para os dois corpos e comparar se eu vou obter realmente as librações observadas ou não, ou qual vai ser o diferencial, se com o meu modelo eu vou obter só umas librações que são parecidas com o da Enceladus, então vai ser um modelo que é aplicável para um corpo ou não, então, mas não tem uma explicação, não tem os resultados publicados para explicar por que um tem esse tipo e o outro não. Porque isso tudo vem da estrutura interna totalmente, então são modelos, né? Tem umas hipóteses, mas não tem uma resposta final, né? Não tem.
Certo, obrigado. E o José Ricardo perguntou, e o caso de Titã?
Então, para o Titã, um dos corpos que a gente considera, mas para o Titã não tem medida de librações. Então, os casos que eu estudei, as questões que eu apresentei aqui não são diretamente aplicáveis ao Titã.
Certo.
Mas seria um corpo interessante também, um corpo que provavelmente tem um oceano subterrâneo, então seria interessante também estudar como um dos possíveis corpos que dá para estudar a libração dele, mas a gente não tem medida nesse momento, então seria comparar com os outros modelos, seria comparar com as librações obtidas por outras pessoas, no caso. Então, não vai ter uma missão no futuro próximo, acho que então, por enquanto não vai ter a medida da libração do Titã, então acho que é mais provável para a Europa. Estamos tendo uns resultados, provável que vai ter umas medidas no futuro próximo da missão Juno. Tem uns resultados que não foram publicados, mas tinham uns press releases, quem sabe vai ter uns resultados que vai dar para tentar reproduzir, mas, enfim, no caso do Titã.
Obrigado, Yeva.
Okay.
Bom, o José Ricardo também perguntou se não dá para inverter o modelo, pedi para ele detalhar um pouco a pergunta, mas se você já entender...
Oi? Qual é?
Se não dá para inverter o modelo, imagino que você, a partir dos resultados obtidos, obter um modelo reológico. Seria isso? Eu perguntei para o José.
Não, sim, a ideia seria essa, no final das contas, a ideia seria inverter, porque a gente vai ter uma observação de libração do certo corpo e a gente quer saber a estrutura interna do tal corpo. Então, a ideia finalmente seria inverter certo. Isso. Seria também o objetivo da aprendizagem de máquina, se for usada. Então, a gente daria a libração para a máquina e a gente queria obter o resultado de estrutura interna do corpo, né? Porque o objetivo final é esse, a gente quer olhar embaixo da crosta dos satélites e planetas.
Certo, muito obrigado. Bom, eu acho que é isso, não teve mais pergunta. Bom, queria agradecer então de novo, Yeva, agradecer quem assistiu, quem interagiu com a gente. É isso, obrigado, Yeva.
Obrigada de novo pelo convite. Muito obrigada.
Alexandre, pode encerrar a transmissão.
Tá bom. Certo. Tá bom. Obrigado, Gabriel, pelo convite.
Sim, eu só estava esperando ele confirmar que encerrou a transmissão, mas tudo bem. Obrigado eu também pela apresentação. Tá certo. Então, provavelmente a gente se vê aí daqui a um tempo. Até mais, Yeva. Tchau, tchau.
Até. Tchau. Obrigada.